Good afternoon, everyone. I am Dr. Shikhar Tyagi. I am back again with another R codings and examples for factor analysis. So we are going to discuss about few more examples on factor analysis and their different type of tests and other things. So here we have another example for the customer satisfaction where we have the correlation matrix. Okay, for the customer satisfaction that we build here, that we give in the R3. We build one matrix. In C, here we provided the data set. Okay. And we made it a 5 by 5 matrix, 5 by 5 correlation matrix. So it will look like this. So this is the matrix: quality, durability, friendly, speed, resolution. So resolution. So this is the matrix. So in the matrix, we created the matrix here. Okay, and see here, combine the data set. All right. So it took the 25 overall values that is arranged in the 5 by 5 matrix. So this is a correlation matrix, and one on the diagonal means each variable is perfectly correlated with itself, and values like 0.85, 0.3, 0.75, and 0.7 shows the strong correlation between some service related variables. Uh, Here in the columns name R3, we assign the column names for each matrix so output is easier to read. After that, in a FA3, we apply the factional function command. So this runs the maximum likelihood factor analysis. So there are different type of methods to find out the estimates in the factor analysis for your loadings and your uh, variance of your error term through the least square method or principal component analysis method or maximum likelihood method. So factnl command apply to find out the estimates through the maximum likelihood method. So here covmat equals to R3. We took this tells us that R3 is a covariance or correlation matrix rather than the raw data, and factor equals to 2 means we are going to request for the two factors here. So and rotations equals to where variance max. So apply the very max rotations, and that means basically an orthogonal rotation that makes loading easier to interpret it by pushing variables strong towards one factor or the other one. And n dot of equals to 200 means number of observation assumed in the sample is 200. So this is the needed because when you give a matrix instead of a raw data, R still need a sample size for the chi-square test. Okay, so after that we will print the FA3 here. Wait. So this is your outputs. Okay. Here you have the uniqueness, loadings, and factors. Okay. So uniqueness is basically 0. For the quality is 0.272. For durability it is 0.005. For friendly it is 0.298. For speed it is 0.200. For resolution it is 0.378. So these are the proportions of the variance in each variable, not explained by the common factors. So formula is basically uniqueness equals to 1 minus communality. So how we are going to interpret it, that small uniqueness means that the variable is well explained by the factors, like durability has the values 0.005. So means almost all of its variance is explained by the two factors, and resolution is 0.378. That is the maximum among all. It means that about 37.8% is unexplained by the factor model. Okay. So after that, we have the loadings for factor 1 and factor 2, that is 0.162, 0.133, 0.826, 0.875, 0.787 for factor 1. For factor 2, 0.0838, 0.989, 0.142, 0.185. So our loading is the relationship between the variable and the factor, that is your lambda ij. Okay, that we in the principal component analysis we apply as the your eigenvalues. So quality and the durability loadings strongly on the factor 2 here. Okay, and friendly speed and resolution load more on the factor 1. Okay, so these values are very high, these three, so these are highly loading on the factor 1, and first two are highly loading on the factor 2. So two factor may be interpreted as the factor 1 can be represented or interpreted like that the service responsiveness or interpersonal service quality, and factor 2 can be interpreted as the technical or product quality. Okay, so the blank entry for the resolution for factor 2 means its loading is below the printing cutoff or very small, almost negligible. So that's why it is not shown. So after that, you have the SS loadings. So this means sum of the squared loadings for each factor. It tells how much variance each factor explain. For example, for factor 1, it is 2.11. So higher value means that factor explain more total variance. All right. And proportion variance is basically given here as 0.422 for factor 1 and 0.347 for factor 2. It means that factor 1 explains 42.2% of total variance and factor 2 explains 34.7 of the total variance. And after that, we have the cumulative variance, that is 0.422 and 0.769. So this means the two factors together explain 76.9% of the total variance. That is a fairly good result here. After that, we applied the chi-square test. So the test of the hypothesis that two factors are sufficient. Okay. So we apply it to check that whether two factors are sufficient or not. So null hypothesis will be here. The two factors model fits well, and alternative hypothesis will be two factors model is not fit well. Okay, are not fit well. So since the p value is very small, and so the null hypothesis is rejected here. P value is almost negligible. So interpretation of these results will be like the two factors model is not a perfect fit, even though it explains a large amount of the variance. All right. So two factors are not enough here. So variance explained is high, but the model fits suggests that more factors or a different mode may fit better. All right. So even though the variance is high here, cumulative variance is 0.769, it is very high. Even though we need more factors here, okay, that is the case here. After that, we have the commonalities, that is 1 minus uniqueness, okay. So for that one, the command is 1 minus FA3. In the FA3, we need to apply the dollar sign to call the uniqueness. So as I told you, the formula is for the commonalities or uniqueness, the idea the relation between them is the uniqueness equals to 1 minus commonalities, or commonalities equals to 1 minus uniqueness. All right. So for that one, and we are going to round off the value up to the three places. Okay. We are going to round it up to the three decimals. So now the value of the commonality is for the quality 0.728, for durability it is 0.995, for friendly it is 0.702, for speed it is 0.8, for resolution it is 0.622. All right. So the commonality means the proportion of the variables variance explained by the common factor. Okay, so how you are going to interpret this one? So durability has the commonality is 0.995. It means that the factor explains 99.5% of its variance, and resolution equals to 0.622. It means that 62.2% of its variance is explained. All right, that is the meaning of the commonalities here. All right. After that, we have the chi-square test for advocacy. So here we are going to apply the command cat again that we used earlier. So cat we use to print the text or the value together, and slash n we are using here. So that creates a new line, and FA3 dollar statistic will extract the chi-square test statistics, and in the p value we are going to store the FA3 dollar p val, capital P VL. So that will extract the p value, corresponding p value. All right. So we will check this one. All right. This is the value of your chi-square test statistics, and this is your p value. All right. Now we will go for another example here. That is the scree plot and the parallel analysis. So we have the eigenvalues. Okay. So here we just store the hypothetical eigenvalues. This could come from the correlation matrix in factor analysis. So these are the values that we store here. After that, we are going to draw a scree plot. Okay. So in the plot, we are going to use the command plot here. 1 to 6 eigenvalues type B PCH equals to 19, X lab is basically the factor number, Y lab equals to eigenvalues, and main should be scree plots. So here 1 to 6 means factor number 1 to 6, and eigenvalues are on the y-axis. Okay, on the x-axis is your 1 to 6 factor numbers, and eigenvalues on your y-axis. And type B means both point and line should be drawn. And PCH 19 means use the solid circle point. And X lab is for your x-axis. Okay, and Y lab for your y-axis. What is the text should appear on the x-axis and y-axis. All right, and main is for your the title of your plot, and ab line h equals to 1, color equals to red, and type equals to 2 for the Cassier criterion. Okay, so here ab line will add it will add an horizontal line at eigenvalue equals to 1. Okay, and it will be a dash I ITY equals to 2 means it should draw a dot line. After that, text should be there. That is for 1.1 Cassier criterion. Correlation color equals to red, and CX equals to 0.8. So it will add a label near to the dash line. That is Cassier criterion should be appear near to the dash line. And how should we explain it? This one. Now run this command. Okay, this is your code for script load. Okay, how you will explain this one? So on the x-axis, you have the factor numbers 1 to 6. Okay, and y-axis is the row eigenvalues that we have, right? And the dashed red line, this red line, is a horizontal line at the eigenvalue equals to 1. Is the Kessler criterion retain only the factor whose eigenvalue exceed more than 1. All right. So how you are going to interpret this? So factor 1, the eigenvalue is approximate 3.2. So it will retain, means accounts for 3.2 into x, the variance of the one original variables, and factor 2 is eigenvalue will be approximate 1.8. So it will also retain. Okay, and factor 3 eigenvalue is 0.9, that is below 1. So we will not retain it by the Kessler rule, and 4 to 4, 5, 6 all are below 1 and they will also discard. So Kessler criterion recommend only two factors here, and scree elbows also between factor 2 and factor 3 that will confirm the two factors solution. So this graph is ideal for teaching both the elbow rule and the Kessler criterion simultaneously, as they agree here. In practice, they sometimes disagree. For example, the elbow might suggest one factor while Kessler says two. So stress that the Kessler criterion only apply when PCA is run on the correlation matrix, that is standardized variables. So that is your escape plot with the Kessler criterion. Okay. Now we will move to the another things of this plot. Oh, sorry, of this example. So after that we have the cumulative variance. So to find the cumulative variance, we apply the command cum sum, and we will store these values in the cum underscore variance. So that will be the cumulative sum of the eigenvalues divided by the sum of the total eigenvalues. All right. So we will get here cumulative proportion, right? And we are going to call print the values with the command cat, the cumulative variance, and we are going to round the cumulative variance. Uh, first we are going to find out in the percentage and route to one decimal place. All right, so we will check what is the output here for the cumulative variance. That is 45.7, 71.4, 84.3, 92.9, 97.1, and 100%. All right. So first factor explains 45.7% of the variance, and first two factors explain 71.4%, and first three explain the 84.3. So here two factors already explain a large number of total variance. Okay, so that is your cumulative variance. So for the parallel analysis for the real data, we need to apply the PSYCH library. So we don't have the data right now, so we are not going to apply that one right now. So for that one, the command is fa.parallel data. You need to fit the data, and in the FM you need to put ML. Okay. right? So we will move to the another example. Example 6. Okay. In the example 6, we have a data of the student test scores of two factors. Okay. So here in R6, we create a matrix of 6 by 6 correlation matrix for the student scores. So we have the marks of the math, physics, chemistry, and English, history, geography. Right. So we are going to see the matrix for our data set. So R6 will be after giving the name. So here, how we will interpret this one? So we can see that math, physics, chemistry are strongly correlated. All right. Math, physics, and chemistry are strongly correlated, while English, history, and geography are highly correlated. Okay, English, history, and geography are highly correlated. Okay, so this suggests that two different academic dimensions, so science and humanities. So after that, we are going to apply the factional command on the covariance matrix R6 and factor equals to 2, and rotation is Varimax, and n dot observation is 150. So after that, we will print the F6 here. We have already explained the factional command. Okay, so uniqueness is 0 for mathematics is 0.346, for physics 0.202, for chemistry 0.292, for English 0.401, for history 0.294, and for geography it is 0.42432. So this shows how much each subject is not explained by two factors. So physics has the low uniqueness, and so it is well explained, and geography has the higher uniqueness. So a moderate portion remains unexplained. So after that we have the loadings for factor 1 and factor 2. That is for mathematics, for factor 1 it is 0.792, physics 0.886, for chemistry 0.824, for English 0.13, for history 0.103, for geography 0.230. For factor 2, mathematics has 0.161, physics 0.114, for chemistry 0.171, for English 0.762, for history 0.834, for geography 0.718. So here factor 1 and factor 2, you can see that in factor 1 all science subjects, math, physics, chemistry, have the high loadings. So factor 1 can be interpreted as the science performance, and for factor 2 the English, history, and geography has the higher loadings. So factor 2 can be interpreted as the humanities performance. So the first three variables are loading heavy on factor 1, and last three loads heavily on factor 2. So this is the exactly the kind of clean pattern we want in the factor analysis. So after that we have the SS loadings, that is our sum of square of loadings. All right. So that is 2.713 and 1.86, right? After that, we have the proportion of the variance, that is 0.362 and 0.310. So factor 1 explains 36.2% of the variance, and factor 2 explains 31% of the variance. And together, both of them, they explained 67.2% of the variance. Okay. So after that, we have the chi-square test. So the chi-square test statistics is 4.42 with 4 degrees of freedom. All right. And the This is important because since the p-value is greater than 0.05, so we do not reject the null hypothesis that two factors are sufficient. So unlike the example 3, this model is considered as an adequate fit. All right. So this was for factor 3. So this is your result. After that, we are going to print the manual p-value. All right. So it will simply explain that p-value is large, so two-factor model fits the data reasonably well. Okay. Thank you so much. Other examples we will solve in the next class. Okay, subscribe for the future videos. Thank you very much.